Well, we shall start this basis and dimension of a vector space, and also we will find rank and matrix inverse. So, basically a basis is very important thing for a vector space, that a basis characterizes a vector space, or in other words a basis is a shortcut representation of a vector space. If basis of a vector space is known, then we can find the vector space itself by taking all possible finite linear combination of elements in B. So, let us define a basis first. So, basis of a vector space. So, let V be a vector space over F a subset S of V is called a basis for V if the following two conditions hold, that is V is a this S is a linearly independent set and second condition is that S spans V, that is L of S is equal to V. That in other words, that every element of V can be expressed as a finite linear combination of elements in S. So, let us see some examples. Of course, before that we shall define dimension of a vector space, that if V contains a finite basis B, then V is called a finite dimensional vector space, and dimension of V are denoted by dimension of V is the number of vectors in B. If V is not finite dimensional, then it is called an infinite dimensional vector space. Let us see some examples. That first example is like this. This set consisting of vectors 2, 0, 6, 1, 2, minus 4, 3, 2, 2 is not a basis for R3, because this is not a linearly independent set, because this is not a linearly independent set, that one can write this third vector as sum of the other two, that is this 3 2 2, this can be written as sum of these two vectors 2 0 6 plus 1 2 minus 4. Another example is that this set consisting of vectors 2 0 0 3 4 0 is also not a basis for R3, because it does not span R3, that is any element in the z axis, that is any vector of the form that 0 0 z cannot be expressed as a linear combination of vectors in this set. So, another example, third example is like this. However, this set, that is consist of vectors like 1 0 0 0 1 0 0 up to this 0 0 1, where each vector is an n tuple, each element is an n tuple. This set is a basis for Rn. One can easily check that this set of vectors forms a linearly independent set. One can also write in echelon form and check this, and obviously any vector we take in Rn, that can be written as linear combination of these vectors. So, this basis is called the standard basis of Rn. This basis is called the standard basis of Rn. So, therefore, dimension of this vector space Rn is equal to, therefore, dimension of Rn is equal to n. We will see another example, that here we consider all polynomials over a field f. Consider the space of all polynomials over f, that is P f. So, the P f is an infinite dimensional vector space, because this set consisting of 1 x, x square, x cube is a linearly independent set, and it spans the space Pf. However, this Pnf, that is the set of all polynomials over f of degree less than or equal to n, is a finite dimensional vector space. And this set, that 1 x, x square up to xn, is a basis for Pnf. Hence, dimension of Pnf is equal to n plus 1. We will see another example of a basis, that is example 5. Here this dimension of the vector space R 2 cross 2, that is the set of all 2 by 2 real matrices is equal to 4, because this set consisting of matrices 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1 is a basis for this R 2 cross 2. Similarly, dimension of R m cross n is equal to m n, where R m cross n is the collection of all m by n real matrices. So, we will see more examples while proceeding this topic later on. So, next we shall see some well known results for finite dimensional vector spaces. We may not able to prove them, but we may refer those results, and they are also very important results. So, all those results we shall write here in a theorem, so that we can say that properties of a finite dimensional vector space of a finite dimensional vector space. So, here we will write as a theorem. So, let V be an n dimensional vector space over a field F, then the following are true. So, first one is that every basis contains n number of vectors. Every basis of V contains n number of vectors. Second property is like this: every set of n plus 1 or more vectors in V is a linearly dependent set. Linearly dependent set. Third result is like this: if S is a linearly independent set, and it consists of n vectors, then S is a basis for V. Fourth property is that if S is a set of n vectors and L of S is equal to V, that is S spans V, then S is a basis for V. So, here this property third and fourth says that when can a set of vectors be a basis for a finite dimensional vector space, then this fifth property is like this, that if S is a set of m vectors, S is a set of m linearly independent vectors, that is S is consist of vectors v1, v2 to vm, and m is less than or equal to n, then S can be extended to a basis for V. That is, there exist vectors say um plus 1 up to un such that this set consisting of vectors v1, v2 to vm um plus 1 up to un is a basis for V. Similarly, we have another property, that is sixth one, that if S is consist of k number of vectors, say w1, w2 up to Wk, k is greater than or equal to n and L of S is equal to V, that is S spans V, then S contains a basis for V. Another property is that for every subspace, that if W is a subspace of this vector space V, then dimension of W is less than or equal to dimension of V. So, let us see one example to check whether a given set of vectors is a basis or not. So, let us see this example. Here we will show that this set B consists of vectors 1, 0, minus 1, 1, 1, 1, 1, 2, 4 is a basis for R3 in two different ways. So, here actually we shall use that result 3 and 4 of the previous theorem for this checking. So, this first we shall show that S is a linearly independent set. So, our first method is to show that B is a linearly independent set. We do this by considering echelon form of these vectors, or in other words we form the matrix like this. Consider the matrix whose rows are the given vectors 1, 0, minus 1, 1, 1, 1 and 1, 2, 4. Converting this to echelon form, we get like this. So, from this matrix we apply elementary row operations and get echelon form of 8. So, applying this R1 replaced by this R2 minus R1, we get this matrix. That is 1, 0. Here we replace this row to 1, 0, minus 1, 0, 1, 2, 1, 2, 4. Then we make this elementary row operation R3, we replace by R3 minus R1 and get this matrix, that is 1, 0, minus 1, 0, 1, 2 and here 0, 2, 5 and once more we apply this elementary row operations and get this matrix, that is we have to make this entry 0 to get in echelon form. So, therefore, we replace this R 3 by R 3 minus twice R 2 and get this matrix 1 0 minus 1 0 1 2 0 0 1. So, notice that this last matrix is in echelon form and here no 0 row is there. So, here this last matrix, the last matrix is in echelon form and here no 0 row is there and no row is the 0 row. So, the vectors in B are linearly independent and hence B is a basis for R 3. So, the second method is to show that B spans R 3. This will work because B is consist of 3 vectors and dimension of R 3 is also 3. So, therefore, if we show that B spans R 3, then B will be a basis for R 3. So, B spans R 3 means if we consider any arbitrary vector in R 3, that we should able to write as a linear combination of vectors in B. So, let x 1, x 2, x 3 be an arbitrary vector in R 3. So, we shall write this arbitrary vector x 1, x 2, R 3 as a linear combination of vectors in B. So, let us consider this linear combination x 1, x 2, x 3 and that we write as alpha times 1 0 minus 1 plus beta times 1 1 1 plus gamma times 1 2 4. Here alpha beta gamma comes from this real field or their scalars. So, here we shall find the values of alpha beta gamma. We shall find the values of alpha beta gamma. So, from here we get this equation. So, let us say this be 1, So, from this equation 1 we get alpha plus beta plus gamma is equal to x 1 and this beta plus twice gamma is equal to x 2 and minus alpha plus beta plus 4 gamma is equal to x 3. On solving for alpha beta gamma, we get alpha is equal to twice x 1 minus 3 x 2 plus x 3, beta is equal to minus twice x 1 plus 5 x 2 minus 2 x 3, and gamma is equal to x 1 minus twice x 2 plus x 3. So, that means given any arbitrary vector x 1, x 2, x 3, we can find alpha, beta, gamma in terms of this known values x 1, x 2, x 3. So, that this x 1, x 2, x 3 can be written as a linear combination of these vectors. So, therefore, this B spans R3 and hence B is a basis. So, B spans R3 and is consist of 3 vectors. Hence, B is a basis for R3. So, next we shall find out another important terminology, that is rank of a matrix, and that rank of a matrix is also very useful. So, here we shall find this rank of a matrix, and that we find again in terms of this linearly independent vectors. So, let Aij be a matrix of size m by n matrix over F. The rank of A is the maximum number of linearly independent rows in A. Of course, one can also take that rank of a matrix as the maximum number of linearly independent columns. So, all those properties we can write as a remark that the rank of a matrix A is also defined as the maximum number of linearly independent columns in A. Hence, rank of A is equal to rank of its transpose. So, second of remark is like this: rank of a matrix A is equal to 0 if and only if A is the 0 matrix, that is all the entries in A are 0. And then this another way that is the third one can this third remark that one can find rank of a matrix from echelon form of this also, or one can define rank of a matrix in this fashion also. So, that is the rank of A is the total number of non-zero rows in the row echelon form of A. In fact, we use this third remark to find rank of a matrix, and so this is useful. So, let us see one example that determines rank of a matrix. So, the example is like this. Here we determination of rank. So, consider this matrix. Here we find rank of this matrix, that is entries are 3 0 2 2 minus 6 42 24 54 21 minus 21 0 minus 15. So, we will convert this matrix to echelon form. We convert this to row echelon form, that is this given matrix is 3 0 2 2 minus 6 42 24 54 21 minus 21 0 minus 15. So, here we apply this elementary row operation and make this position 0. So, here we shall apply this row operation, that R2 second row we replace by R2 plus twice R1 first row, 2 times R1, R2 plus 2 R1. So, we get this matrix 3 0 2 2 0 42 28 58, and the third row is as it is, that is 21 minus 21 0 minus 15. So, again we apply this elementary row operation, that here this third row, first entry of third row, we make that 0. So, therefore, we replace row 3 by this row 3 minus 7 times row 1. So, we get this matrix like this. So, first row is 3 0 2 2 0, 42, 28, 58, and here we get this 0, minus 21, minus 14, and this minus 29, minus 29. So, this is not yet in echelon form, that second entry in third row, that we have to make 0. So, here we apply this elementary row operation. R3 we replace by R3 plus this half of row 2, and we get this matrix with 3, 0, 2, 2, 0, 42, 28, 58, and this third row will be completely 0. So, the last matrix is in echelon form, and number of non-zero rows here is equal to 2. So, the rank of this given matrix is therefore 2. So, the number of non-zero row in the echelon form is 2. Hence, the rank of the given matrix is equal to 2. So, this is how we find rank of a matrix by applying this echelon form of it. So, next we shall find out inverse of a matrix, that is inverse of a matrix. So, here we consider square matrices only. So, recall that we define inverse of a matrix like this. Let A be n by n matrix. A matrix B of size n by n is called inverse of A if this AB is equal to BA is equal to this n by n identity matrix. If inverse of a matrix A exists, then it is unique. If inverse of A exists, then it is unique and denoted by A inverse. So, inverse of all square matrices may not exist. Here in the following theorem, we give a necessary and sufficient condition for existence of inverse of a matrix. So, let A be a matrix of size n by n, then A inverse exists if and only if A is of full rank, or in other words rank of A is equal to n. So, this gives a necessary and sufficient condition for existence of inverse of a matrix. So, here we give a method to find inverse of a matrix, and that method is very famous one, that is called this Gauss-Jordan elimination method. So, we discuss about this Gauss-Jordan elimination method to find inverse of a matrix. To find inverse of a matrix. So, here we consider that whether the first we check whether the matrix has full rank or not, and we write this method in the following steps. So, let A be n by n matrix. So, first step is to check whether this A is of full rank or not. If rank of A is equal to n, then go to next step, otherwise the inverse of A, otherwise the inverse of A does not exist. So, this second step is like this. Here we form an augmented matrix like this, form an augmented matrix AI where A is where A is the given matrix and I is the n by n identity matrix. So, third step is that we apply elementary row operations to this augmented matrix and make this first n columns upper triangular, that apply elementary row operations to AI, to this AI to make first n columns upper triangular. Let the resultant matrix be U k, where U is in upper triangular, U is an upper triangular matrix. Then fourth step is again we apply elementary row operations to UK and get the first n columns as identity matrix. So, again apply elementary row operations to this augmented matrix UK and get the identity matrix, in the first n columns. Let the resultant matrix be IL. Then L is equal to A inverse. This matrix L will be inverse of the given matrix. Let us take one example and check these steps in this process. So, let us consider one example where we find inverse of a matrix by applying this Gauss-Jordan elimination method, that find inverse of this matrix A, that is given by 2 0 minus 1 5 1 0 0 1 3. So, first we shall check whether this matrix A is of full rank or not. So, we will get echelon form of this matrix like this, and echelon form of the matrix A is given by this 2 0 minus 1 0 2 5 0 0 1. So, rank of A is equal to 3 and A inverse exists. Then we follow the steps given in the Gauss-Jordan elimination method and form this augmented matrix. In the first 3 columns we consider the matrix 0 2 0 minus 1, the given matrix, 5 1 0 0 1 3, and here we consider identity matrix, that 1 0 0 0 1 0 0 0 1, and we apply elementary row operations to make this first 3 columns upper triangular. So, we get this matrix, that first we divide first row by 2, so that we will get this first entry be equal to 1. So, that is R1 is replaced by half of R1, and here we get this matrix B 1 0 minus half 0 0, and this is 5 1 0 0 1 0, there this 0 1 3 0 0 1. Then again we apply elementary row operations to make this entry, first entry in the second row is equal to 0. So, therefore, we apply this operation that R 2 we replace by R 2 minus 5 R 1 and get this matrix B like this. So, it is 1 0 minus half 0 0 0 1 5 by 2 minus 5 by 2 1 0 0 1 3 0 0 1. So, next again we will apply elementary row operations that we shall replace this R 3 by R 3 minus R 2, that makes the second entry in third row is equal to 0 and we get this matrix B like this. So, first row is this 1 0 minus half 0 0 0 1 5 by 2 minus 5 by 2 1 0. The second row we have kept as it is and this third row will be 0 0 half 5 by 2 minus 1 and 1. So, now this augmented matrix is of the form that first 3 rows they form upper triangular matrix. Upper triangular matrix means all entries below the main diagonal they are equal to 0. So, next we shall again apply elementary row operations and make this first 3 columns in identity matrix and it is like this. From there again we apply elementary row operations R 1 replaced by this R 1 plus R 3 to make third entry of first row is 0. So, we get this is 1 0 0 3 minus 1 1 0 1 5 by 2 minus 5 by 2 1 0 0 0 half 5 by 2 minus 1 and 1. So, next we shall make third entry in the second row, that is equal to 0. So, we apply this elementary row operations that R 2 we replace by R 2 minus 5 R 3 and get the matrix B like this. Here we get this 1 0 0 3 minus 1 1 and 0 1. Okay. So, here we get this as 0 1 0 minus 15 6 minus 5 and this 0 0, half, 5 by 2, minus 1, 1. So, finally, we multiply this row 3 by this 2. So, row 3 we replace by twice row 3 and get this matrix 1 0 0 3 minus 1 1 0 1 0 minus 15 6 minus 5 0 0 1 and 5 minus 2 2. So, this is the required form that the first 3 columns form identity matrix. So, A inverse is this matrix 3 minus 1 1 minus 15 6 minus 5 5 minus 2 2. So, this is how we find inverse of a matrix by applying the Gauss-Jordan elimination method, and this method is very useful and one can implement in a computer also and find inverse of a matrix. That is all for this lecture. We will stop here.